makes isosceles and right triangles special. Then we'll introduce you to polygons and quadrilaterals, a type of polygon that gets its own group. A square is a quadrilateral, but a triangle isn't. Why? Well, stay tuned and find out on the many...
Before we move on, let's make sure we've got the basics.
There are three ways to describe triangles by their sides: equilateral, with 3 congruent sides; isosceles, with 2 congruent sides; and scalene, with no congruent sides. We have 4 ways to describe triangles by their angles. If they have 3 congruent angles, they're equiangular. If they have 3 acute angles, they're acute triangles. If they have 1 right angle, they're right triangles. If they have 1 obtuse, they're obtuse triangles.
Corresponding parts of congruent triangles are congruent. This is also known as CPC-TC. We can also prove the congruence of triangles with the side-side-side postulate, the side-angle-side postulate, and the angle-side-angle postulate.
The angle-angle-side theorem says that if we know 2 angles and a non-included side of 2 triangles are congruent, then the 2 triangles are congruent. With right triangles, we can use hypotenuse-leg theorem, which says that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and one leg of another right triangle, then the triangles are congruent.
Pythagoras, the man.
One of the biggest moments in geometry occurred back in the 6th BC when Pythagoras proved the Pythagorean theorem. That's a good thing, especially because the Pythagorean theorem was named in his honor. Let's learn a little bit about this amazing man.
Pythagoras was my friend for 37 years. We would discuss things for hours on end. I think we met in the 6th century BC. I knew the man like I knew the back of my hand. Oh, and one more thing. Pythagoras knew math.
Section D, isosceles and right triangle theorems.
So now that we have a good footing of triangles, let's look at a couple of special types of triangles: the isosceles triangle and the right triangle.
We'll begin with the isosceles triangle. Remember isosceles triangle basics? An isosceles triangle is a triangle with 2 congruent sides. These 2 sides are called the legs. The third side is called the base. The angles formed by the base and legs are called the base angles, and the third angle is called the vertex angle.
Let's do a proof.
Given that sides AB and AC are congruent, prove that base angles B and C of isosceles triangle ABC are congruent.
First, we'll get started by stating our given information. Sides AB and AC are congruent.
Second, we'll draw AD, the bisector of angle A.
Why do we do this? We need a way to use one of our newly learned triangle postulates: side, 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 angle, side, angle, or side, angle, side. Our reason is every angle has exactly 1 bisector.
The definition of an angle bisector allows us to state that angle DAB is congruent to angle DAC.
We can prove that side AD is congruent to side AD because of the reflexive property. Boy, that reflexive property sure is great.
We have 2 pairs of sides and the pair of included angles. So triangle ABD is congruent to ACD because of the side angle side postulate.
Now we can state our goal. Angle B is congruent to angle C because corresponding parts of congruent triangles are congruent, or CP-CTC. Done.
So we've proven that the base angles of an isosceles triangle are congruent. Let's try another theorem that'll prove that the legs opposite those congruent angles are also congruent.
We're given that angles B and C are congruent, and we want to prove that legs AB and AC are congruent in isosceles triangle ABC. Let's get started.
First, we'll state our given information. Angle B is congruent to angle C.
Next, we draw AD, the bisector of angle A, because every angle has exactly 1 bisector. I'm telling you, this is the key. Now, we've got 2 triangles to work with, and we're in business.
By the definition of an angle bisector, we know that angles BAD and CAD are congruent.
So far, this proof is really similar to the one we just did, which is fine, but we're going to change it up now.
Because we've just established that the two angles at the top are congruent and angles B and C are congruent, we know the third pair of angles must be congruent too. Our fourth step is to state the congruence of angles ADB and ADC. This is because the sum of angular measures is 180.
We want to use the angle-side-angle postulate. We have all the angles we'll need. Now we just need a side length.
To give us a congruent pair of sides, we state AD is congruent to AD. This is because of the reflexive property. There it is again, real handy.
Now we can state that triangle ABD is congruent to triangle ACD because of the angle-side-angle postulate.
Finally, we can say that AB is congruent to AC because corresponding parts of congruent triangles are congruent, or CPC-TC, and we've proven our theorem.
Nice job! In addition to our three postulates, there's a theorem we can use to prove triangles congruent. You may have noticed in our last example that having two pairs of angles and one pair of non-included sides congruent is good enough to prove congruent triangles. So here's our new theorem.
The angle-angle-side theorem says that if two angles and a non-included side of a triangle are congruent to the two corresponding angles and non-included side of another triangle, then the two triangles are congruent.
Angle-angle-side is a good theorem to remember, but you won't use it as often as the side-side-side, angle-side-angle, or side-angle-side postulates, so we won't take the time to prove it. Just keep it in your back pocket for later.
Just like a free lunch or a peace treaty called NITO, there's no such thing as a side-side angle theorem. Here's why. This is an example of two triangles with congruent pairs of sides and a congruent pair of non-included angles. But the triangles are certainly not congruent. They're not even in the same ballpark.
For right triangles, there's a special theorem we can use to prove them congruent. It's called the hypotenuse leg, or HL theorem. Take a look.
To describe the hypotenuse leg theorem, we need to review a couple of terms related to right triangles. First, the two sides which form the right angle are called the legs. The side opposite a right angle and the longest side of a right triangle is called the hypotenuse. So, the hypotenuse leg, or HL theorem, states that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then the two right triangles are congruent.
So let's consider the hypotenuse leg theorem with right triangles TUB and HOP here. We know that their hypotenuses are both 5 inches, and they each have a leg that is 3 inches. So, because they're right triangles, they're congruent because of the hypotenuse leg theorem.
There are 3 ways to describe triangles by their sides: equilateral with 3 congruent sides, isosceles with 2 congruent sides, and scalene with no congruent sides. We have 4 ways to describe triangles by their angles. If they have 3 congruent angles, they're equiangular. If they have 3 acute angles, they're acute triangles. If they have 1 right angle, they're right triangles. If they have 1 obtuse angle, they're obtuse triangles.
Corresponding parts of congruent triangles are congruent. This is also known as CPC-TC. We can also prove the congruence of triangles with the side-side-side postulate, the side-angle-side postulate, and the angle-side-angle postulate.
The angle-angle-side theorem says that if we know 2 angles and a non-included side of 2 triangles are congruent, then the 2 triangles are congruent. With right triangles, we can use the hypotenuse leg theorem, which says that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and one leg of another right triangle, then the triangles are congruent.
Part 1, the real world, quadrilaterals, other polygons, and student loan officers.
Section A, general definitions.
A 3-sided polygon is a triangle. A 4-sided polygon is a quadrilateral. A 5-sided polygon is a pentagon. A 6-sided polygon is a hexagon. An 8-sided polygon is an octagon. An n-sided polygon is an n-gon.
Like this report giver said, a polygon is a simple, closed, multi-sided figure with line segments for sides. We name a polygon by listing its vertices in order. The vertices are all the corners. For instance, this pentagon could be named PENTA, or ATNEP, or TAPEN. Now let's go over a few more definitions that go with polygons.
A convex region occurs within a polygon when a segment connecting any two inner points never crosses the edges, like this figure here. For any 2 points, A and B, the segment connecting them is completely inside the figure. A convex polygon never caves in on itself. Here's an example where the region is not convex. See how the shape sort of caves in on itself? That's concave. We can pick 2 points in the region, say points C and D, and the segment connecting them crosses the edges and goes outside the region, where point X lies.
A diagonal is a segment which connects two non-consecutive vertices. In this diagram, BE and BD are diagonals. We couldn't draw a diagonal from B to A because segment BA is already part of the polygon. That's why diagonals must be from non-consecutive vertices. B and A are consecutive vertices.
A regular polygon has all sides and angles congruent. We seldom find regular polygons in nature. Most regular polygons are man-made, like this perfectly square man-made dealie found here.
Now that we know the shapes and definitions, we can use them and a little more information to figure out the sum of the measures of the angles inside each shape. I hope you're as excited as I am.
We know that the measures of the angles in a triangle total 180 degrees. Let's look at this quadrilateral. We can cut it into two triangles. So the sum of the measures of its angles is 180 times 2, which is 360 degrees. Let's try a pentagon. We can divide it into 3 triangles. So the sum of the measures of its angles is 180 degrees times 3, 540 degrees. How about a hexagon? We can divide it into 4 triangles. There's a simple pattern developing. The number of triangles a polygon can be divided into is always 2 less than the number of sides. So, our theorem is the sum of the measures of the angles in a convex polygon with n sides is n minus 2 times 180 degrees.
Now that we know some general information about polygons, let's get specific. We've got some secret information about quadrilaterals. We're going to give it to you now. Once you watch this part of the tape, eat it.